So let's take a look at strategy for testing series. Now in this video we'll be looking at several different series problems and testing for convergence or divergence using most if not all of the series tests that we have learned in this chapter. So for these next set of problems, let's go ahead and test the series for convergence or divergence. So for number 1 we have the infinite series from n equals 1 to infinity of n squared minus 1 over n squared plus n. Now the very first thing I notice right away is if I set the limit of this sequence to infinity, I will obviously get 1. So if I go ahead and do that, we have the limit as n approaches infinity of n squared minus 1 over n squared plus n. In this case, we're just looking at, once again, the significant or the highest degrees of the numerator and denominator. So the highest degree of the numerator is n squared, highest degree of the denominator is also n squared. Because they are the same degree, we just take the ratio of the coefficients. Obviously that's just going to be 1 over 1, which means that the limit equals 1. The limit is 1, which is not equal to 0, and because the limit does not equal 0, we know the series will diverge because or by the divergence test, or the test for divergence. Now for number 2, we have the series from n equals 1 to infinity of 1 over n squared plus n. Now obviously in this case we can't use a divergence test because the limit is going to be equal to 0. It doesn't look like geometric series, but if I take a look at the denominator of the sequence here, the most significant term here is n squared because that's the highest degree. So what I would actually do in this case is do a direct comparison test, so dct, to the infinite series from 1 to infinity of just 1 over n squared. Now we know 1 over n squared converges by the p-test because obviously p, the exponent in this case, is 2, and 2 is going to be greater than 1. And because 2 is greater than 1, obviously it converges. Now let's go ahead and actually compare both of those series. So we have 1 over n squared plus n, and then 1 over n squared. Now in order to find which one is greater, we can just cross multiply. So we have 1 times n squared, which is n squared, and then we have 1 times n squared plus n, which is n squared plus n. Now obviously because we have that extra n there, n squared plus n is going to be greater than n squared, which tells us that 1 over n squared is also greater than 1 over n squared plus n. Now 1 over n squared converges, which means anything less will converge as well. Because 1 over n squared plus n is less than 1 over n squared, this series also converges by, well in this case we use the direct comparison test. So it converges by the dct. Now for number 3 we have the series from n equals 1 to infinity of negative 3 to the n plus 1 power over 2 to the 3n power. Now the very first thing I would do is, I'm not really looking for any series right now, or series tests, but what I'm actually looking to do first is to actually simplify what's inside the series. So negative 3 here, we have it raised to the n plus 1 power. Because there's a plus sign separating the two exponents, I can rewrite it as negative 3 to the n times negative 3 to the first, or just negative 3. And then over, well 2 to the 3n, I can rewrite it as 2 cubed to the n power. Because when you have a power to a power, you multiply. So now I'll bring that negative 3 outside of the fraction and rewrite it as negative 3 times, up top we have negative 3 to the n, over 2 cubed, which is 8, so 8 to the n. Now because both the numerator and denominator have the same exponents, we can factor that exponent out. So we still have negative 3 outside the fraction, and then we have times, well we factor out negative 3 over 8 from that exponent, and we get negative 3 over 8, the entire thing raised to the n power. Because remember, when we have a fraction raised to a certain power, we can distribute that power both to the numerator and denominator of the fraction. So now I can go ahead and rewrite the series from n equals 1 to infinity of negative 3 times negative 3 over 8 raised to the n power. And so realize that because we have a ratio here, or a fraction raised to some power n, this is a geometric series test. Now remember, in the geometric series test, if the absolute value of the ratio r, in other words what's inside the parentheses that's taken to the power, is less than 1, we know the series will converge, and if the absolute value of the ratio r is greater than or equal to 1, then the series will diverge. In this case, the absolute value of r, or the absolute value of negative 3/8, is going to be 3/8. 3/8 is obviously less than 1, so we know the series will converge. And it will converge once again by the geometric series test, or just GST. Now in order to find what this geometric series actually converges to, we can just use a simple formula where we take a sub 1 over 1 minus r. Now a sub 1 is just the first term in the sequence, so if we calculate a sub 1, Once again, we start at n equals 1, so all we have to do is plug in 1 for n, and we get negative 3 times negative 3/8 of the first is just negative 3/8. Notice negatives will cancel, and so the first term is going to be 9 over 8. So we have 9 over 8 as a sub 1 over 1 minus r. Once again, r is just a ratio, and the ratio is negative 3/8. So minus negative 3/8 means plus 3/8. Now if we go ahead and simplify here, we have 9 over 8 divided by 1 plus 3 over 8, or 8 over 8 plus 3 over 8 is 11 over 8. Dividing by 11 over 8 is the same thing as multiplying by its reciprocal. Notice the 8's will cancel, and so this geometric series converges to the exact value of 9 over 11. Now for number 4, we have the infinite series from n equals 2 to infinity of 1 over n times the square root of ln n. Now in this case, I see that I can do the integral of this, and before we do the integral test, we have to make sure that this function is decreasing, continuous, and positive. So if I change the variables from n to x, we have 1 over x times the square root of ln x. This function obviously is bottom heavy, so it's decreasing. It is continuous from 2 to infinity, and it is positive and above the x-axis, so we can use the integral test. So we take the integral of 1 over x times the square root of ln x times dx from our bounds, obviously from 2 to infinity. And then we can go ahead and evaluate. Now in order to evaluate, we have to use u substitution. So I'll make u equal to ln of x. So then du, or the derivative of ln x, is 1 over x dx. And if I isolate dx, dx is going to equal to x times du. If I go ahead and replace everything back into the integral, we have the integral from 2 to infinity of 1 over x times the square root of u, because once again we made u equal to the natural log of x, times dx, which once again is equal to x times du. Realizes the x's will cancel, so what we have left is the integral from 2 to infinity of 1 over the square root of u, which I can rewrite as u to the negative 1/2 times du. Now the integral of u to the negative 1/2 is going to be 2u to the 1/2. I can go ahead and replace back the u. So then we have 2 times the square root of ln x, or 2 times ln x to the 1/2 power. And then we can go ahead and evaluate from our bounds of 2 to infinity. Now when I evaluate here, obviously 2 is just a constant. So we have 2 times, when I plug in infinity for x, we have the square root of ln of infinity, minus when I plug in 2 for x, we have the square root of ln of 2. So then we have 2 times the square root of natural log of infinity. Now if you think about it, natural log of infinity is basically going to be infinity, because natural log of x just grows on and on forever. So we have the square root of infinity, which is still going to be infinity, and then minus the square root of natural log of 2. Now natural log of 2, or the square root of natural log of 2, is insignificant compared to infinity. So we'll basically have 2 times infinity, which still remains as infinity. So because the integral diverges, that means the series will also diverge by, well, we use the integral test this time. So it diverges by the integral test. Now for number 5, we have the infinite series from k equals 1 to infinity of k squared times e to the negative k. So what I would actually do here first is bring that negative exponent to the denominator. So I'll rewrite it as the series from k equals 1 to infinity of k squared divided by e to the k. Now because we do have exponents, it's probably a good idea to use the ratio test in this case. Now once again, let's say we have the series of a sub n. Now in a ratio test, we're going to take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. So let's go ahead and apply that same formula to the series that we were given. So in this case, we're going to take the limit as n approaches infinity of the absolute value. This time we don't have n as our variable, but we have k as our variable. So we're going to take k plus 1 squared over e to the k plus 1, and then divide by the original series, or the original sequence itself. Now dividing by k squared over e to the k is the same thing as multiplying by the reciprocal. So multiply by e to the k over k squared. So rewriting the limit here, the limit as n approaches infinity of the absolute value. Now k plus 1 squared, I'll just leave it as it is. So we have k plus 1 squared over, now e to the k plus 1, I'll separate that using properties of exponents to e to the k times e to the first, or just e. And then we have times e to the k over k squared. So realize in this case that e to the k's will cancel, and what we're left with is the limit as n approaches infinity of the absolute value of k plus 1 squared over e to the first times k squared. Now in order to find the limit, I'll actually FOIL k plus 1 squared. So then we'll get k squared plus 2k and then plus 1 over, we still have e, which is the coefficient of k squared. So once again we have the absolute value and we have the limit as n approaches infinity. Now if we're approaching infinity here, we're basically looking at the significant degrees of the numerator and denominator. So the significant degree, or the highest degree of the numerator, is k squared, and the highest degree of the denominator is k squared as well. Because they have the same degree, we just take the ratio of the coefficients of the highest degrees. So that's just going to be 1 over e. So that's going to be the limit. Now 1 over e is obviously less than 1, and because it's less than 1, we know that this series is convergent. By this time we use the ratio test. Now for number 6, we have the series from n equals 2 to infinity of negative 1 to the n plus 1 over n times the natural log of n. So realize in this case we do have an alternator here, negative 1 to the n plus 1 power. So it's a pretty good idea to use the alternating series test. So remember, in the alternating series test, all we have to do is take the limit to infinity, so the limit as n approaches infinity, of everything inside the series except for the alternator. So if we cancel out the alternator, all we have left is the limit of 1 over n times the natural log of n. Obviously this fraction is bottom heavy, so the limit to infinity is going to be equal to 0. And because it's equal to 0, we know that this series will converge by the alternating series test. Now let's test for absolute convergence. Now remember, when we test for absolute convergence, we take the infinite series, the same bounds here, n equals 2 to infinity, and we take the infinite series of everything but the alternator. So we're just going to test the infinite series of 1 over n times the natural log of n. Now in this case, this is a decreasing, continuous, and positive function if we graph it as 1 over x times the natural log of x, so we can use the integral test. So if I take the integral of 1 over, I'll change the variable from n to x, from 2 to infinity, times dx. This is similar to one of the previous problems that we did, where we're going to set u first equal to the natural log of x, so then du equals the derivative of natural log, which is 1 over x dx. So once again, dx is equal to x times du. If I go ahead and sub everything back into the integral, we get the integral from 2 to infinity of 1 over x times u, once again u is equal to natural log of x, times dx, which is equal to x times du. Realize the x's will cancel, and all we're left with is the integral from 2 to infinity of 1 over u times du. The integral of 1 over u is the natural log absolute value of u, and I can go ahead and replace back the u of ln x. So what we really get here is ln absolute value of another ln of x. Now let's go ahead and evaluate from the bounds of 2 to infinity. So when I plug in infinity, we get the natural log absolute value of natural log of infinity, and then minus when I plug in 2, we get the natural log absolute value of natural log of 2. Now as mentioned before, ln of infinity is basically infinity, so then we have another ln of infinity, which is going to be infinity as well. So we have infinity minus the natural log of the natural log, or absolute natural log of 2. In this case, the natural log absolute value natural log of 2 is insignificant compared to infinity, so infinity minus that is just going to give us infinity. Now because the integral diverges to infinity, this tells us that the series also diverges by the integral test, so by it. And so the original series problem, once again, was the infinite series from n equals 2 to infinity of negative 1 to the n plus 1 over, we had n times the natural log of n. Now, as mentioned before, the original series converges by the alternating series test, but the series without the alternator diverges, which tells us that the original series is not absolute convergent, but conditionally convergent. Now for number 7, we have the series from 1 to infinity of 3 to the n times n squared over n factorial. Because we do have a bunch of exponents and factorials, it's probably a good idea to use the ratio test. So once again, in the ratio test, we set the limit as n approaches infinity of the absolute value, so we make everything n plus 1 instead of just n. So we have 3 to the n plus 1 times n plus 1 squared over n plus 1 factorial. And then we divide by the original sequence itself, but dividing by 3 to the n times n squared over n factorial is the same thing as multiplying by its reciprocal. So multiply by n factorial over 3 to the n times n squared. Now I'm going to skip the limit for right now and come back to it later. I'm just trying to simplify what's inside of the absolute value. So starting off with the numerator of the left fraction here, 3 to the n plus 1, I can separate that using properties of exponents once again into 3 to the n times 3 to the first, or just 3. And then we obviously have times n plus 1 squared, I'll leave that alone, over n plus 1 factorial, I can rewrite it as n plus 1, or I can expand it as n plus 1 times n factorial. And then we have times n factorial, I'll just leave it as it is, over 3 to the n times n squared, I'll leave those as they are right now. So now realize that 3 to the n's will cancel, the n factorials will cancel, and so what we're left with here, I'll come back to the limit now, is the limit as n approaches infinity of the absolute value of what we have simplified this entire thing down to, which is 3 times n plus 1 squared over, we have n plus 1 times n squared. Now realize that one of these n plus 1's can go away, so now we have simplified it down to the limit as n approaches infinity of the absolute value of 3 times n plus 1. Now actually distribute the 3, so I'll just rewrite it as 3n plus 3 over, we have n squared. Now notice this is a bottom heavy fraction, so the limit to infinity is going to be 0. And because 0 is less than 1, this series will converge by the ratio test. Now for number 8, we have the series from 1 to infinity of negative 1 to the n times 2 to the 1 over n power. In this case, we do have an alternator, so it's a good idea to use the alternating series test. Once again, in the alternating series test, we're going to set the limit as n approaches infinity of everything but the alternator. So if we cancel out the alternator, all we have left is 2 to the 1 over n power. Now in this case, we can just use direct substitution and directly sub in infinity for n, so we get 2 to the 1 over infinity. Now 1 over infinity, or 1 over a very large number, is basically going to get closer and closer to 0. So we have 2 to the 0 power, and anything to 0 is obviously going to be equal to 1. Now once again, we use the alternating series test, and 1 does not equal 0. Now keep in mind, because the limit does not equal 0, it does not converge by the alternating series test. But keep in mind, the alternating series test is only a test for convergence, not for divergence. So we cannot say it diverges by the alternating series test. We can only say whether or not it converges. So we have to use another test, and usually, if it does not converge by the alternating series test, it diverges by the divergence test. So we just say it diverges, or the series diverges, by the test for divergence. So I'll just label that as dt. Now for number 9, we have the series from 1 to infinity of negative 1 to the n times ln n over the square root of n. Once again, because we have an alternator here, we can use the alternating series test. We're going to set the limit as n approaches infinity of everything but the alternator, so ln of n over the square root of n. Now, in this case, we need to figure out which one is a faster growing function, ln n or the square root of n. If you use your graphing calculator and actually graph it, the square root of n is a faster growing function than the natural log of n, which tells us that this fraction is bottom heavy. Because it's bottom heavy, the limit to infinity is going to equal 0. Obviously 0 does equal 0, so this series will converge by the alternating series test. Now for number 10, we have the infinite series from n equals 1 to infinity of negative 2 to the 2n power over n to the n. Now I can rewrite this numerator as negative 2 squared to the n power, because once again, when we have a power to a power, we can multiply, and we'll get back to that, over n to the n. Now because, I'll actually put this in brackets, because we have the same exponent on the numerator and denominator, I can factor out that exponent and rewrite it as, we have negative 2 squared, which is 4, so 4 over n, the entire thing raised to the n power. So now rewriting the series, we have the infinite series from n equals 1 to infinity of, once again, 4 over n, the entire thing raised to the n. Now because we have an exponent n, and there's a variable inside as well, it's probably a good idea to use the root test. So once again, in the root test, we're going to take the limit as n approaches infinity of the absolute value of the nth root of whatever's inside the series. So in this case, we would take the nth root of 4 over n to the n power. Now this is good because the nth root of something raised to the n power will cancel. So all we're left with is the limit as n approaches infinity of the absolute value of 4 over n. Now in this case we do have a bottom heavy function. So when we plug in infinity, we have the absolute value of 4 over infinity. Now 4 over infinity is basically going to be 0, and the absolute value of 0 is 0. Obviously 0 is less than 1, and because it's less than 1, we know the series will converge, this time by the root test. Now for number 11, we have the series from n equals 1 to infinity of tangent of 1 over n. Now if I were allowed to use a graphing calculator, I would actually go ahead and graph tangent of 1 over x. And if you actually graph that, you would see that it's very similar to the graph of 1 over x itself. So I would actually do a direct comparison test of the series of tangent of 1 over n to the infinite series of 1 over n itself, from 1 to infinity. Now we know the infinite series of 1 over n from 1 to infinity diverges by the p-test. That's a divergent harmonic series because once again the exponent is 1. Now if I go ahead and compare these two, we have tangent of 1 over n compared to 1 over n itself. So I'll put tangent 1 over n over 1 compared, I'll rewrite 1 over n once again to compare to 1 over n. Now to find which one's bigger, let's just go ahead and cross multiply. So we get n times tangent of 1 over n, and then we get 1 times 1, which is 1. Now the thing is, if you plug in a really large number for n here, let's say we plug in 1,000, you would actually get the answer of 1. And so 1 and 1 are obviously equal to each other. So this test is actually inconclusive. We cannot use a direct comparison test because we cannot find one function to be greater than the other. So in this case, I'm going to switch to go from the direct comparison test to the limit comparison test. In this case, we will be able to find whether the series converges or diverges. So once again, in the limit comparison test, we take the limit as n approaches infinity. Once again, we're still comparing it to the series of 1 over n. We can take any function first, so let's just take tangent of 1 over n and divide that by the other sequence here, 1 over n. Now in this case, I'm not going to bring the 1 over n to the numerator, because if I use direct substitution here, we have tangent of 1 over infinity over 1 over infinity. Now 1 over infinity is basically 0, and tangent of 0 is 0, 1 over infinity obviously is 0. Because we have 0 over 0, we can use L'Hopital's rule, where we take the derivative of the numerator and the denominator. So the derivative of tangent of 1 over n is secant squared of 1 over n times the derivative of 1 over n, which is going to be negative 1 over n squared. And then divide it by the derivative of 1 over n. Obviously that's still going to be negative 1 over n squared. So realize both of these will cancel. What we're left with is the limit as n approaches infinity of secant squared of 1 over n. So now I can go ahead and use direct substitution. We will get secant squared of 1 over infinity. 1 over infinity once again is 0. So then I can rewrite it as secant of 0, the entire thing squared. Now secant of 0 is just going to be 1, and 1 squared is 1. Now by using the limit test, or the limit comparison test, because our limit 1 is greater than 0, and is a finite value, and the comparison diverges, the original series we got also diverges. And this time by the limit comparison test. Now for number 12, we have the series from 1 to infinity of n factorial over e to the n squared. Now because we do have factorials and exponents, probably a good idea to use the ratio test. Once again, we'll set the limit as n approaches infinity of the absolute value of, we have n plus 1 factorial. Once again, we're going to put every n variable as n plus 1 over e to the n plus 1 squared. And then we're going to divide by the sequence itself. Dividing by that sequence is the same thing as multiplying by its reciprocal. So multiply by e to the n squared over n factorial. Now in order to simplify, I'm going to come back to the limit for right now. We have n plus 1 factorial, which can be rewritten or expanded into n plus 1 times n factorial over, we have e to the n plus 1 squared. So I can rewrite that as e to the, I'll FOIL it, and say n squared plus 2n plus 1. And then we have times e to the n squared over, obviously, n factorial. Now realize the n factorials will cancel, and I can simplify this even further. Because we have pluses in the exponents, I can break it up into several different exponents. So we have n plus 1 over, now I'll rewrite it as e to the n squared times e to the 2n, and then times e to the first, or just e. And then we multiply obviously by e to the n squared. Now realize the e to the n squareds will cancel, and so we're left with the limit as n approaches infinity of the absolute value of n plus 1 over e to the 2n times e. Now e to the first, we can just rewrite it like that, and because we have the same basis, we can just add the exponents. So we have the limit as n approaches infinity of n plus 1, we have the absolute value over e to the 2n plus 1. Now obviously e to the 2n plus 1 is a much faster growing function than just n plus 1 itself, so we do have a bottom heavy fraction, so the limit to infinity is going to be equal to 0. Obviously 0 is less than 1, so we know that the series, the original series of n factorial over e to the n squared will converge, this time by the ratio test. Now for number 13, we have this infinite series from n equals 1 to infinity of the nth root of 2 minus 1, the entire thing raised to the nth power. Now because we have the nth power here, it's probably a good idea to use the root test. So in this case, we take the limit as n approaches infinity of the absolute value of the nth root of the entire thing inside the series. So the nth root of 2 minus 1, and then to the nth power. Once again, the good thing here is the nth root of something raised to the n power will cancel. So all we're left with is the limit as n approaches infinity, the absolute value of the nth root of 2 minus 1. Now what I'm going to do is go ahead and rewrite the nth root of 2 as 2 to the 1 over n power. So we have the limit as n approaches infinity of the absolute value of 2 to the 1 over n minus 1. Now if I go ahead and use direct substitution, we then get 2 to the 1 over infinity minus 1. Now 1 over infinity, obviously 0. 2 to the 0 is 1, so 1 minus 1 gives us 0. Obviously 0 is less than 1, so we can say that the original series here converges by the root test, because once again the limit is less than 1. Now for number 14, we have the infinite series from 1 to infinity of n over n plus 1 raised to the n squared power. So I'm actually going to go ahead and rewrite it as the series from n equals 1 to infinity of n over n plus 1 to the n, and then taken again to the n power. Now because we have a power to a power, obviously we multiply and we get right back there. So what I would do in this case is go ahead and use the root test again. So in this case, once again, we have the limit as n approaches infinity of the absolute value of the nth root of n over n plus 1 to the n, and then raised to the n again. I'll go ahead and include brackets there. Now the nth root and the n power will cancel, and what we're left with is the limit as n approaches infinity of the absolute value of n over n plus 1 raised to the n power. Now in order to evaluate this limit, I'm actually going to go ahead and set this equal to some constant c, because we know the limit is going to be some value, and in this case we'll just label it as c for right now. We'll find what that value is later. Now the next thing I would do is go ahead and natural log both sides. So we get the limit as n approaches infinity of the absolute value of the natural log of n over n plus 1 raised to the n power, and that's going to equal the natural log of c. Now using properties of logs, I can bring this exponent in front of the natural log. So then we have the limit as n approaches infinity, absolute value of n times the natural log of n over n plus 1, and so that's going to equal the natural log of c. Now I'm going to come back to the LNC later, but first let's focus on the limit, the left side of the equation. So if I go ahead and rewrite the limit as n approaches infinity, absolute value, now I'm going to go ahead and rewrite what's inside the absolute value as ln of n over n plus 1, and I'm going to divide that by 1 over n. Now because we have two functions, one function being divided by another, we can take the limit of each individual function. So if I start by taking the limit of, or the limit as n approaches infinity of the natural log of n over n plus 1, realize that the highest degree of the numerator is the same as the highest degree of the denominator, so we just take the ratio of the coefficients. 1 over 1 is obviously just going to be 1. So the limit of the numerator is the natural log of 1. Don't forget we do have the absolute value. Over, we have the limit as n approaches infinity of 1 over n. I can just go ahead and plug in infinity, and 1 over infinity is basically 0. Now ln of 1 is 0, so we do get 0 over 0, which means that we can use L'Hopital's rule. Now once again, in L'Hopital's rule, we're going to take the derivative of the numerator and the derivative of the denominator. Now in order to derive ln of n over n plus 1, now let's say you're trying to take the derivative of the natural log of some inside function u. Well, in this case the derivative is going to be u prime over u. So the very first thing we have to do is to take the derivative of n over n plus 1. In this case we just have to use the quotient rule. So once again we take the lower function times the derivative of the higher function, derivative of n is just 1, minus the top function times the derivative of the lower function, derivative of n plus 1 is just going to be 1, all over the lower function squared. So we took the derivative of that inside function and then we divide that by the inside function itself. So divide it by n over n plus 1. And then we obviously take the derivative of the denominator, and the derivative of 1 over n is just going to be negative 1 over n squared. Now this is obviously confusing at first, but let's actually break this up. So let's focus on this part right now. We'll come back to the negative 1 over n squared later. So now n plus 1 times 1 is just going to be n plus 1. And then we have minus n times 1, which is n. N minus n cancel, and we just have 1. So we have 1 over n plus 1 squared, and then divide by n over n plus 1. Dividing by n over n plus 1 is the same thing as multiplying by the reciprocal, so n plus 1 over n. Now realize one of the n plus 1s will cancel, and what we're left with is 1 over n times n plus 1. Now don't forget we do have the negative 1 over n squared on the very bottom, so now we can go ahead and divide by negative 1 over n squared, or multiply by its reciprocal, so n squared over negative 1. Now realize that one of the n's will cancel, and so what we're left with here is the limit as n approaches infinity of the absolute value of this entire thing, which we have simplified down to just this. So that is going to be negative n over just n plus 1. So now all we have to do is take the limit to infinity. In this case the highest degree of the numerator is the same as the highest degree of the denominator. So we just take the ratio of the coefficients of the highest degrees. So that's negative 1 over 1, which is going to be equal to negative 1. Now be careful here, because the limit obviously is negative 1, but earlier on we set that equal to the natural log of c. So now we say that negative 1 equals the natural log of c. So in order to find what that limit is, or in order to find what c is, we just e both sides. That will cancel, and we get that c equals e to the negative first, or 1 over e. Now remember, we did use the root test to test the series. Now e to the negative first, or 1 over e, is obviously less than 0. And because it's less than 0, we get that the series converges by the root test.